In this video, we are going to talk about foundations for inference. In particular, we're going to look at point estimates and sampling variability. This is our overview slide, which we'll spend about 5 minutes going over before going over each topic in more detail and with more examples. We start by talking about sampling, and at this point we assume that the sampling has been done. So the related chapter, chapter 1.3, Sampling Principles and Strategies, was talking about how to conduct a survey and how to choose your sample. Once that is done, we come to this chapter where we're going to use the sample estimate to approximate a population parameter. So when the parameter is a proportion, it is often denoted by lowercase p and the sample proportion as p hat. And this is how it's pronounced, p hat. So the idea is there's a population that's too big for us to go and survey every person, but we're interested in some sort of measurement or number about that population. That's called our parameter. And if it's a proportion, in other words, what percentage of people, then we don't denote that population parameter with a p, and we sample to try to see, to approximate our population parameter. And so our sample proportion is going to be p hat. And unless we collect responses from every individual in the population, p will remain unknown, but we will use our sample p hat as our estimate of p. The error in the estimate is the difference between the sample estimate and the parameter, and generally the error consists of two aspects, sampling error and bias. We'll talk briefly about sampling error, sometimes called sampling uncertainty, and it describes how much an estimate will tend to vary from one sample to the next. So sample size denoted n will help us quantify this error. So bias is a type of systematic tendency to over or underestimate the true population value. And we try to minimize bias through the thoughtful data collection procedures as discussed in Chapter 1, in particular 1.3. In the previous chapter and videos, we talked about different probability distributions, including the normal distribution. So in this case, we can have a sampling distribution by sampling thousands of times. Once we sample thousands of times, we will have thousands of sample proportions, p hats, and then we can plot them to make a distribution of sample proportions. So of course, this isn't something you want to do if you're trying to estimate a population parameter. This is something we do when we study what sampling distributions look like. So again, it's not practical, but we can simulate a data set that we know that we actually can make ourselves, and then we can sample thousands of times so that we can study what sampling distributions look like. One, we find that the center of the distribution will be equal to the population parameter, which is good. That means the mean of multiple samples will lead to the population parameter. Two, the spread, we're going to measure that by something called standard error. It is very similar to standard deviation. And the formula is right over here. It's our next topic. And then three, the shape resembles a normal distribution. So everything we talked about in our previous video about normal distribution applies to our sampling and inference. So if you have forgotten or did not look at the normal distribution video, I would strongly suggest you do so. And what this study of sampling distribution gives us is the central limit theorem and the success-failure condition. So when observations are independent and the sample size is sufficiently large, so these are two conditions we must meet. One, the observations must be independent, and two, our sample size must be sufficiently large. Then the sample proportion p hat will tend to follow a normal distribution with the following mean and standard error. So the mean of p hat is going to equal to our population parameter. And the standard error of p hat is equal to the square root of p times 1 minus p over n, where n is the sample size. And again, p is our population parameter. So the sample size is typically considered sufficiently large when n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. And this is often called the success-failure condition. So one of these two things must be greater than 10, so n times p. If you think of p in a binomial sense, p is the probability of success, then 1 minus p is probability of failure, which is where we get the name success-failure. So either the success times the sample size or the failure times the sample size must be greater than or equal to 10. So our success-failure condition is what we use to satisfy this criteria here, too, the sample size is sufficiently large. To satisfy this first criteria, the observations are independent. We have some help over here that they're independent. One, if we're talking about subjects in an experiment, they're considered independent if they undergo random assignment to the treatment and control groups. Two, if we have an experiment where observations are from a simple random sample, so it's kind of equivalent to drawing names or numbers out of a hat, equivalent to random draws, then they are considered independent. And three, if a sample is from a seemingly random process, you can use your judgment. And again, some of this getting independent samples comes from chapter 1.3, where we talked about the strategies for sampling and getting a good sample. And that covers our overview, so we'll come back up and we'll take a closer look at sampling. So once we've taken a sample, we can use a sample estimate to approximate a population parameter. So the number that we're interested in that concerns the entire population is called the population parameter. Then the number from our sample that we use to estimate the population parameter is called the sample estimate. So when a parameter is a proportion, such as a percentage, it is often denoted by lowercase p, then the sample proportion is known as p hat. Unless we collect responses from every individual in the population, p, the population parameter, is going to remain unknown, but we're going to use p hat from our sample estimate, as our estimate of p. And the error in the estimate is the difference between the sample estimate and the parameter. Generally, the error consists of two aspects, sampling error and bias. Our first example, suppose a poll suggests the U.S. president's approval rating is 45%. So here it's a proportion, it's 0.45 or 45%. We would consider 45% to be a point estimate of the approval rating we might see if we collected responses from the entire population. So again, we haven't asked everyone in the U.S. population, that would be millions of people, but we had a poll that sampled from the population. So this entire population response is generally referred to as the parameter of interest. So the president's approval rating, if we could sample the entire population, we would get our parameter of interest, which is the proportion of people who approve of the U.S. president's performance. So let's just write that down. The parameter of interest is the proportion of the U.S. population that approves of the U.S. president's performance. So again, that's the proportion if we could sample or survey everyone in the U.S. We would get P, the proportion of the U.S. population that approve. We can't actually ask everyone in the U.S. population. That would be a tremendous effort. So we have P hat, which is from our sample, and that's our estimate, our sample's estimate of P. And then we have P minus P hat is equal to our sampling error. This is something we cannot calculate directly because P is unknown, but we have ways of estimating this. And I just want to then bring in this second topic of sampling error, since we talked about it. Sometimes called sampling uncertainty, describes how much an estimate will tend to vary from one sample to the next. Sample size denoted N will help us quantify this error. So there's sampling error and there's bias, which is a systematic tendency to over or underestimate the true population value. We try to minimize bias through thoughtful data collection procedures, as we discussed in Chapter 1. Remember, we can't actually calculate sample error because we don't know P. The whole point of sampling is we can't survey the entire population. But what we can do is we can study the process of sampling. So we study and we create what we call a sampling distribution, which is the distribution of sample proportions produced by sampling thousands of times. So what we do is we create a known data set, a known population, maybe in Excel. We can just, for this, like in our last example, we talked about people who approved of the president's performance. So maybe we might have 10,000 entries in our Excel sheet, and they'll be yes or no, depending, yes being they approve, no being they don't. But we'll know what our 10,000 Excel sheet entries are. So we'll know the actual proportion of people who said yes in our Excel sheet. But we're going to take multiple samples and study what happens to those samples. And what we will find is, one, the center of the distribution. When we put up all of our samples and all of the estimates, we'll find the center of the distribution of our estimates will be equal to the population parameter. And two, the spread can be measured by standard error, where we have our equation here. So again, this is how we can start talking about sampling error. And three, the shape will resemble a normal distribution. So the example that your book used to study sampling distribution is the proportion of American adults that support the expansion of solar energy. And they say the parameter is equal to 0.88, which is our parameter of interest. So if we take a poll of 1,000 American adults on this topic, the estimate would probably not be perfectly 0.88, but how close can we expect the sample proportion of our poll to be to 0.88 or 88%? So in this example, we know that the actual parameter value is 88%. So we can experiment how close the sample will get to 88%. And we do this by simulating a sample of approximately 250 million American adults. And that's the population of the US in 2018. So we simulate by writing on 250 million pieces of paper. And 88% of those 250 million pieces of paper will say approve, and the remaining 12% of the 250 million pieces of paper will say do not approve. And then we'll mix the pieces of paper and pull out 1,000 of the pieces of paper to resemble a sample of 1,000 American adults. And then we compute our sample estimate from the 1,000 pieces of paper. And we'll do this 1,000 times. So the thing is, we're not actually going to write on 250 million pieces of paper. We're going to use a computer simulation to simulate, well, in this case, it's an Excel sheet of maybe, or some program of 250 million yeses or nos. And of the 250 yeses or nos, 80% are going to say yes or approve, and 12% will say no or do not approve. And then again, our computer simulation is randomly going to choose 1,000, our sample size will be 1,000 of the pieces of paper. We take the 1,000 pieces of papers and then we calculate what percentage of those 1,000 pieces of paper say approved, and that will be our sample p-hat, our sample estimate. And it should come close to 0.88. We can do this 1,000 times until we have a distribution of 1,000 p-hats, and we can plot that. And your book says, well, we run the simulation many times. I just said 1,000 times. And then we create a distribution of sample proportions. So if we run the simulation 1,000 times, let's say 5,000 times, we're going to have 5,000 sample proportions. And then we put it on a distribution like we had in our previous video. We create a histogram, and we call it the sampling distribution. And we can characterize the sampling distribution as follows: center, spread, and shape. And what people studying statistics have found is if we run the simulation enough times, so they said 10,000, I said, 1,000, I said 5,000. Anyway, 10,000 times, we expect the center of our sampling distribution to be the same as our population parameter. Remember, we know our population parameter because we wrote it down on those pieces of paper or in our computer simulation. So the center of our sampling distribution will be the same as our population parameter, in this example 88%. The spread will be measured in standard deviations or standard error. Usually we use standard error. And the shape resembles a normal distribution. So again, this is how we study how sampling works. And what we see is if you have a big enough sample and also you have independent samples, you will see that this is what happens is you'll get your population parameter, the center of your sampling distribution will be the same as the population parameter. You can measure the error and standard error, and you will get a normal distribution. So these are things that we now know. So in real-world applications, we never actually observe the sampling distribution, but this is useful for understanding point estimates that we observe. In other words, this is what people do when they're studying statistics, and it gives us the tools, it gives us the information so that we then can conduct samples and know that we can use our point estimate as a good estimate of the population. We have a way of estimating error, and we also have, we know that we're going to be in a normal distribution, which we will then later use for our inferences. So here your book says that we had that computer simulation of 250 million pieces of paper, and then we did 10,000 different samples, and then each of those samples produced an estimate, our sample proportion, or our sample estimate, which we then can put in a histogram, and you'll see that this histogram starts to resemble a normal curve, and it will be centered at our actual population parameter. And your book says a histogram of 10,000 sample proportions where each sample is taken from a population where the population proportion is 0.88 and the sample size is n equals 1,000. A question: if we use a much smaller sample size of n equals 50, would you guess the standard error for p hat would be larger or smaller than if we used n equals 1,000? And intuitively, it would seem more data is better, and generally that is correct, and we'll see why when we take a closer look at the formula for standard error. So the people who studied sampling techniques, who ran that kind of simulation, all of their results is summarized by the central limit theorem here. So we're going to start the central limit theorem and the success failure condition. So when observations are independent and the sample size is sufficiently large, so these are our two conditions that need to be met if we want to use the central limit theorem on our samples, our sample estimates. One, the observations have to be independent, and two, the sample size must be sufficiently large. The sample proportion p hat will tend to follow a normal distribution with the following mean and standard error. So the mean, that's the mu of p hat, will equal to p, our population parameter. And the standard error of p hat is equal to the square root of p times 1 minus p over n. Now let's take a closer look at these two conditions that must be met in order to use the central limit theorem on our samples. First, observations are independent. So this is this note over here. So one case where you can say observations are independent, if we have subjects in an experiment, it's considered independent if they undergo random assignment to the treatment and control groups. Another case that we can consider independent observations are from a simple random sample, which is equivalent to random draws. Those are considered independent. And three, if a sample is from a seemingly random process, you can use your judgment. And again, chapter 1.3 talked about different sampling methods so that we could have an independent observation. The second criteria we need to fulfill is that the sample size must be sufficiently large. And here we have this condition called the success failure condition. The sample size is typically considered sufficiently large when n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. One of these have to be true. Either n times p or n times 1 minus p must be greater than or equal to 10. If you consider p, the proportion, to be something like the Bernoulli trials, where p is the probability of success, then 1 minus p is going to be the probability of failure, which is where we get the success failure name of the success failure condition. So probability of success times n must be greater than or equal to 10. Or, I'm sorry, the probability of failure times n must be greater than or equal to 10. Earlier, we had estimated the mean and standard deviation of p hat using the simulated data when p equals 0.88 and n equals 1,000. So now we want to confirm the central limit theorem applies, and therefore the sampling distribution is approximately normal. So to find that confirm that the central limit theorem applies, we have to show that the two conditions, independent and sample size sufficiently large, are met. So we need to check independence and the success failure condition over here that guarantees a sufficiently large sample size. First, for independent, well, each trial is independent as they are equivalent to a simple random sample or independent draws. Because we've done this using computers, we say let's just draw from our population at random. Looking at our success failure condition, n times p, so n equals 1,000 times p, which is 0.88, equals 880, which is greater than or equal to 10. And n times 1 minus p, that's 1,000 times 0.12, is equal to 120, which is greater than or equal to 10. So now we can use the central limit theorem, which I abbreviated CLT, and the central limit theorem says the sampling distribution will be normal. Now we want to compute the theoretical mean and standard error of p hat when, I need to put the hat, when we know p is equal to 0.88 and n equals 1,000. We will use our central limit theorem, which then is going to tell us that the mean of our p hat is going to equal to p. So the mean of p hat will equal to p, which is 0.88, and the standard error of p hat is equal to the square root of p, 0.88, times 1 minus 0.88 or 0.12 divided by n. In this case, n is 1,000, so our standard error is 0.01. This next part will rely on your knowledge of the normal distribution. And the normal distribution is something, if you haven't looked at it or forgotten, you really do need to review it because it's important from here on and also through the rest of this chapter as we talk about inferences. So the question is, estimate how frequently the sample proportion p hat should be within 2% of the population value p equals 0.88. And remember, our data is normally distributed. So if p equals 0.88 for n equals 1,000, we already calculated here our standard error of p hat is equal to 0.01. If our proportion, remember, is 0.88 or 88%, to be within 2%, we could either be at 88% minus 2% or 0.88 minus 2.02, or we can go as high as 88% plus an additional 2%, and we're still within 2% of 0.88, right, if we add 0.02. So 0.88 plus 0.02. So in other words, as long as p hat is between 0.86 and 0.9, we're within 2% of 0.88. And now we use everything we learned from the normal distribution. We compute our z-score for 0.86. So first, this top part here tells us how far away our 0.86 is from the mean. It's simply 0.86 minus our mean, 0.88. So that's 0.02, right? 0.86 is 0.02 units away from the mean, negative point because it's smaller. Then we divide by our standard error. And when we talked about the normal, we talked about the standard deviation. We're just going to substitute standard error. So we're -2 standard errors away from the mean. We can calculate our z-score for 0.9. So first we look at how many units 0.9 is away from our mean, which is 0.02, and it's positive because it's larger. We divide by our standard error, so we're 2 standard errors above the mean. So looking at our normal distribution, here, this z-score equals -2, and this z-score is equal to 2. We can look up by table our z-score of 2, and we'll find that 95.4% of our data is between z-score -2 and 2, which means 95.4% of the time, the sample p hat will be within 2% of the population parameter P. The other thing we can do is remember our 68, 95, 99% rule that said that 68% of our data will be between -1 and 1 standard deviation. In other words, 68% of our data is within 1 standard deviation of the mean, 95% of our data is within 2 standard deviations, and 99.7% of our data is between 3 standard deviations. So again, approximately 95% of the time, the sample p hat will be within 2% of p. Again, if you haven't reviewed or you don't remember the normal distribution, now's a good time. Oh, and now we're going to explain how the formula for standard error, which is over here, shows that a smaller sample, n, would produce a less reliable estimate. So let's take a look at our standard error formula. So when n is larger, we're dividing by a larger number, which gives us a smaller number here, and when we square root, it's smaller. So dividing by a larger n will give you a smaller standard error. These next questions are sort of to some technical details. So what happens when the sample size is not sufficiently large? That is, NP is less than 10, or n times 1 minus p is less than 10. In this case, for the success-failure condition not to be met, if either this fails or this fails, then the whole thing fails, because for the success-failure condition to be met, both of them have to be met. So if either one fails, that's why I have an or here, then the condition is not met. And we can study this with simulation of different sizes, just like we did before, where the true proportion, let's say, is p equals 2.5, and we can use a sample size of 10. So note, in this case, n times p is 10 times 0.25, which is 2.5, which is less than 10, not less than 0. And n times 1 minus p, that's n is still 10, and 1 minus p is 0.75, so 10 times 0.75 is 7.5, which is less than 10. So in this case, both conditions fail. We can then simulate a sample size of 10, so maybe, again, a proportion of yes or no. It might be no, no, yes, yes, no, 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 no. So there should be 10 of these, and our proportion is 2 out of 10 is equal to yes. So our first sample estimates p hat, our estimate p hat is equal to 0.2. Now we can study this by doing this 1,000 times. Now let's say we do this sample 10,000 times. We'll get 10,000 different p hats or different estimates. We can plot them in a histogram. And what we can see is, for this histogram, we can compute a standard error. We can look at a normal curve with the center of p equals 0.25 and standard error over here. And this is what a normal curve would look like. So we can compare what we got with the sample that's too small versus a normal curve. This would be if the sample were sufficiently large. So when the sample size is not sufficiently large, one, we see the distribution is more discrete, right, than continuous. If it were continuous, we'd have, all these little samples in between, so it'd be all full, so it would just be this curve. But instead, we have kind of chunks, like histogram bins. And second, the skew in the distribution is more noteworthy. Certainly, it's not this symmetric curve that we have of a normal distribution. If anything, it looks like it's skewed a little bit to the right. There's this tail to the right. And the other things we can notice is the sampling distribution always centered at the population parameter p means the sample proportion is unbiased when the data are independent. And the variability in the sampling distribution decreases as the sample size becomes larger. And last, for a particular sample size, the variability will be largest when p equals 0.5. A last note, the strategy of using sample statistics to estimate a population parameter is quite common, and it's a strategy we can apply to other statistics other than just a proportion. So before we were looking at a percentage that we were trying to estimate, but we can just straight up estimate some number, such as the average salary for graduates from a particular college. We could survey a random sample of recent graduates, and in that example, we would be using a sample mean for, the average salary, a sample mean, to estimate the population mean for all the graduates. To review what we covered in this video, we talked about sampling and using a sample estimate to approximate a population parameter. So when a parameter is a proportion or a percentage, it is often denoted by p, and the sample proportion is denoted as p hat. Unless we collect responses from every individual in the population, p is going to remain unknown. But we will use p hat as our estimate of p. And the error in the estimate is the difference between the sample estimate and the parameter. Generally, the error consists of two aspects, sampling error and bias. And so here we have a discussion of sampling error, sometimes called sampling uncertainty, describes how much an estimate will tend to vary from one sample to the next. Sample size, denoted n, will help us quantify this error. We have the formula over here. And the second type of error is bias, which is a systematic tendency to over or underestimate the true population value. And we try to minimize this through thoughtful data collection procedures, as discussed in chapter 1.3 when we talked about sampling principles and strategies. To study sampling techniques, we can come up with a sampling distribution. This is something we don't do when we're just trying to take a sample to estimate a population parameter. But statisticians want to know about the sampling distribution, which will give us information of what we can do, such as using the normal curve. So sampling distributions is the distribution of sample proportions produced by sampling thousands of times. So from simulations, we can characterize sample distributions by 1, the center of the distribution will be equal to the population parameter, 2, the spread will be measured by standard error, and 3, the shape resembles a normal distribution. And these results are summarized in the central limit theorem and the success failure condition. The central limit theorem says when observations are independent and the sample size is sufficiently large, the sample proportion p hat will tend to follow a normal distribution with the following mean and standard error. The mean, that's mu, of p hat will equal to the population parameter p, and the standard error of p hat is equal to the square root of p times 1 minus p, all divided by n. There are two conditions here then we need to satisfy in order to use the central limit theorem. 1, the observations must be independent, and 2, the sample size must be sufficiently large. So to verify that a sample is sufficiently large, we look at n times p, it must be greater than or equal to 10, and n times 1 minus p must be greater than or equal to 10 as well. This is called the success failure condition. And then second, to look at the observations are independent, we have some clues to determine whether our observations are independent. 1, if subjects in an experiment are considered independent if they undergo random assignment to the treatment and control group. 2, you might know that your sample is independent if the observations are from a simple random sample equivalent to random draws. And 3, if your sample is from a seemingly random process, you can use your judgment. So that's it for this video. Thank you for watching.